Hello and welcome to podcast. I believe this is number 12. It's the start of chapter 13 or chapter 3. Wow, off on that. And what we're going to cover is acid base, the basics. So there'll be two parts altogether. This first one deals with some of the things you had in GChem and a few new things you'll need to know for OChem. But wanted to start with the concept of what an acid is, what a base is, get a lot of the definitions down pat. So an acid, we typically think of it as just something that generates H plus, and we typically think of a base as something that generates OH minus. It's a pretty simplistic thing. So KOH, for instance, gives me a lot of OH minus. HNO3, nitric acid, gives me a lot of H plus. Definitions are a little more in depth than that. There's a Arrhenius definition, which describes what they do, their behavior in water. So acid, when added to water, will form hydronium ion. That's an acid. Base, when added, will form hydroxide. So that's one definition, but we also have the Bronsted-Lowry definition, which describes an acid as a proton donor, H plus donor, and a base as a H plus acceptor, proton acceptor. And then we'll go through Lewis, which is an electron pair donor for a base, an electron pair acceptor for an acid. So we will discuss all these. The reality is we're probably going to use the Lewis definition mostly in OChem, but we want to start and make sure we have all three definitions down pat. So we're going to do the water material or the water approach first, and then we'll gradually over the course of this chapter drift into other solvents. So as mentioned, according to the Arrhenius definition, an acid yields H3O plus, hydronium and water. Because it's rich in hydronium, so standard water, due to autoionization, will have 10 to the minus 7 H plus, H3O plus, and 10 to the minus 7 OH minus. It'll associate just a little bit, and the pH will be 7. But in this case, because we've added an acid, it ends up the equilibrium gets shifted, and you have excess H3O plus. So your H3O plus concentration is greater than hydroxide, and because H3O plus is now greater than 10 to the minus 7, the pH drops to below 7. And because the two add to 14, pH and pOH add to 14 at 25 degrees. If the pH is less than 7, the pOH must be greater than 7. And then last but not least, this is seems like a totally random fact, but I still want you to know it. Litmus turns red with acid. This is something we're going to use in lab quite often, so it's important to know that. And good way to remember that, acid and red end in the same letter, D. And just to be complete, base and blue start in the same letter. So we'll look at that in a little more detail. A base yields hydroxide, OH minus, in water. You generate a solution where the hydroxide is in higher concentration than the hydronium, and the pH is now greater than 7, pOH is less than 7, because again, they have to add to 14, and turns litmus blue. These are our basics. Got to know these. These are different ways of saying the exact same thing. Yields H3O plus, so H3O plus is higher than OH minus, meaning pH is less than 7, which causes a solution that's acidic and therefore turns litmus red. Or yields OH minus in water, so hydroxide is a higher concentration than hydronium, resulting in a higher than 7 pH and thus a less than 7 pOH, and it turns litmus blue. Okay, so let me give an example. This is going to be beyond our pay grade at this point in OChem, but I still want to look at it and see what piece of information I can get and hopefully, piece something out of this question. So a few things. Number one, the reactant is drawn above the arrow, so I take some unknown compound X, I treat it with chromic oxide, something rich in O, so an oxidizing agent, and acidic conditions, H2SO4, also oxidative conditions when the whole thing's combined, to generate some compound Y. So I know, based on this rich in oxygen species, that this organic compound X is going to be oxidized and turned into a, more oxidized compound, organic compound. The two things I know about compound Y, it turns litmus paper red and has an IR absorbance of 1708. So let's start with the litmus paper turning red. Red, I know, is an acid, and it ends up there are only two compounds that you're going to find are acidic in organic chemistry. One is known as a carboxylic acid, and although I've drawn benzoic acid with a benzene ring here, could be CH3 and it'd be acetic acid, could be CH3, CH2, propanoic acid. I could do different acids, but I'm just going to focus on this functional group right here being a carboxylic acid. The other case is an OH on a benzene ring. So this OH on a benzene ring, because of resonance, it can pull electron density away and ends up making that H plus just a little more acidic, little less, well, a little more electron poor, for lack of a better phrase. So litmus paper turning it red means I have one of these two. Okay, you can take advantage of either this piece of information or this piece of information next. So if I wanted to use this piece of information, I know that it added bonds to O. So this has 1, 2, 3 bonds to O. So it probably gained, so this compound with 1, 2, 3 bonds to O, if I went backwards, would have only 1 or 2 bonds to O, got oxidized. So that fits with this structure. This one only has 1 bond to O, so it probably wasn't oxidized, because oxidation would have given it more bonds to O and not just 1 from carbon to oxygen. So this one is less likely. And the other piece of information that you may recall from 121 lab is that when you have an IR absorbance around 1700, it means you have a C double bond O. So this confirms a C double bond O. So first off, litmus being red makes it those two compounds. The 1708 means you must have this group. So I have a carboxylic acid. So if that is the case, the compound X, and again, this is something that covers a little of what we're doing now, acid base, but a little of what we're going to do later called oxidation reduction. So chapters 12 and 19 will cover that. But this is what's known as an alcohol, and specifically a primary alcohol, because this carbon has only one other carbon attached. So primary alcohol can be oxidized into a carboxylic acid, which would, because it's an acid, turn litmus red, because the carbonyl will have a peak around 1700. Okay, fair enough. Want to get rid of that information, and let me get rid of what I've drawn. What I know for sure is compound X must have a carbon with at least 1 bond to O on it, on carbon 1 right here, because you had to gain bonds O. So you had to start with at least 1, you gain the second and third. Okay, definitions. Arrhenius definition we mentioned, what happens in water, so yields H3O plus in water, yields hydroxide in water, that's the Arrhenius definition. There's also a definition proton donor, proton acceptor, known as the Bronsted-Lowry. Decent way to remember it, mnemonic is, if you remember, bro, low, pro, do. Bro, low, pro, do means Bronsted, Lowry, proton donor. So for an acid, bro, low, pro, do, I have no pride, works for me. And then Lewis, electron acceptor, electron donor, but I said earlier it was a pair, so you actually have to use 2 electrons to make a bond. So Lewis base has to be able to donate not one, not just a single electron donor, but electron pair donor. And a great way to remember this, if I just draw the word Lewis base, shoot, I missed something. What did I miss? I missed 1, 2 electrons, because you must have an electron pair, 2 electrons, to be a Lewis base. Hopefully that mnemonic helps a little bit. So I'm going to clear that out, toss a couple of examples. So if I have a reaction such as this, where this lone pair of this amine can come in and attack what amounts to be an empty p orbital on aluminum, we have a reaction. Or if I want to look at the empty p orbital on boron, this lone pair of sulfur can come and attack there. Okay, so this is a Lewis acid-base reaction where the lone pair, electron pair of a Lewis base comes in and attacks the open orbital on an electron pair acceptor, Lewis acid. Okay, feeling okay about this. I'm going to get rid of this real quick and add in one last thing, and that is the pH equals negative log of H3O plus. I'm going to toss a little math in here. If I multiply each side by -1, I will get a negative on this side, gets rid of this. And then if I raise it as an exponent, make it a power of 10, 10 to the log of something, 10 to the log are antifunctions, one another, they're opposites. So I end up getting H3O plus equals 10 to the minus pH. So I get that equation. So let me erase this so I can have the third thing go in. So this correlates to that. Finally, pH plus pOH at 25 degrees Celsius is 14. Okay, so more information to pound through. I want to show how something applies in OChem, in terms of acid-base chemistry. We're going to focus very much on the relationship between pH and pKa. This is essential moving forward in OChem and in biochem. And so you covered it a little bit in GChem, but I want to look at it in a little more depth. So here's what the situation is. We have this drug known as aspirin. We take aspirin orally, and we swallow it. Eventually, it's going to end up in the stomach. So orally, this is the form we take. When it gets in the stomach, it's said to be hydrolyzed. So hydro meaning water, lysed means broken. So that means this weak bond here, an ester bond, reacts with water. So that the water hydrolyzes it. So I had water H2O, where an H went to this O, resulting in the phenol. And this OH went to this group, resulting in a carboxylic acid known as acetic acid. So you get hydrolysis, you get this OH here, and this molecule here. This one doesn't really play a role. This is just vinegar. It's in there. We don't have much of it, so I'm just going to ignore it. So I'm going to get rid of that and focus on what remains. So once it's in your stomach, you have a certain pH, this case 2 roughly. Depends on whether you're digesting, might be a little bit higher, a little bit lower. And then you have two groups here that are acidic. So you have to know some pKa's. So I'm going to continually talk about this 5, 10, 15, 20, 25 sort of, I don't know, shortcut, not precise, but help in memorizing numbers. So carboxylic acid, the most acidic group we find in organic acids, pK's around 5. Protonated amines, phenols, and thiols around 10. Alcohols around 15. Hydrogens on a carbon next to a carbonyl, so-called alpha carbonyl, around 20, and alkynes will be around 25. Not perfect. This is not a perfect set of numbers because there's some variation due to substituents on compounds, but in general, this is going to be approximately 5 and approximately 10. Okay, so we have a scenario here. If the pK of the carboxylic acid is 5 and the pK of the phenol is 10, and the pH of the stomach is 2, you have a condition. So I want to just describe this analogous condition and see if we can apply it here. Temperature and melting point. So the environmental condition of temperature and the physical property of the compound temperature correlate. If I were to tell you something had a melting point of 28 degrees and ask you, is it melted or not? You can't answer it. Or if I told you the temperature outside is 30 degrees, is something melted? You cannot answer it. Individual piece of information about environmental conditions, 30 degrees, or melting point 28, individually don't tell me anything. But when you put the two together, you can make a decision. If it's 30 degrees temperature outside in the ambient conditions, the melting point is 28, 30 is above 28, so it will be melted. Equally, if it's 25 out, then 25 is less than 28, so it would remain as a solid. It would still be frozen, or if it's not water, it should just say it's solid, hasn't yet melted. You have to know both conditions. Same thing is true when you deal with pH. An environmental condition describes the solution or the environment surrounding the compound. And pK, which can be thought of, it isn't exactly a physical property, but it still is similar. It describes the strength of a proton in a compound. So if the pH is less than pKa, then we can say the environment feels acidic. Just like if temperature is less than melting point, we can say the environment relative to the compound feels cold. In this case, it feels acidic. If you are acidic, then things will get protonated. So because the pH is less, 2 is less than 5 and 10, the protonated form is the predominant form. So it's going to be protonated at the carboxyl, protonated at the phenol. Okay, perfect. So intuitive reasoning, again, same sort of reasoning. If it feels acidic, then things get protonated. So that fits this. This relationship actually follows a second way of proving it, and that is Anderson-Hasselbalch equation, pH equals pK plus log of base, which is the deprotonated form, over acid, the protonated form. So if this number is low, like 2, and this number is high, like 5, so this is 5 and this is 2, this must be a -3. Log of a number less than 1 is going to be negative. So the denominator, the protonated, has to be large, and the numerator, deprotonated, has to be small. Small number over large number is less than 1. Log number less than 1 is negative. Negative when added to the pK will make a smaller pH. So the math fits for this. So you can do it by math if you want, and come to the conclusion they're protonated, or intuition. pH is lower in pK, so it feels acidic. Acidic things become protonated. Okay, equally, if we have pH higher than pK, so let's do the same relationship here. If pH is higher, then this number, let's say, is in this case is 5 still, and now we have 7.4. 7.4 is greater than 5, so this must be plus a positive number. So the deprotonated form, the numerator, must be greater than the protonated form, the denominator. So we have this relationship. Okay, so let's figure out what the heck's going on and why I'm going through this. When I take aspirin, it goes in my stomach. It's a gastric form. Stomach is around pH 2. It's all well and good. But because this is neutral, and because these two groups are really close, we learned about intermolecular forces, but because these are so close, they're said to be ortho or 1,2 on this ring. This OH can interact with that lone pair, and it can actually hydrogen bond with itself. The more it interacts with itself, the more it can have intramolecular hydrogen bonding, the less it's going to have inter-hydrogen bonding, less it's going to interact with water around it. So its water solubility is actually reduced because it reacts with itself here. And it's a benzene, so it's a lipid. So you got lipid, reduced hydrophilicity, reduced hydrogen bonding with the environment. And then one last piece of the puzzle, double bond, double bond, double bond, double bond carbon. So every single carbon is sp2. This oxygen also sp2. Because of resonance, this can donate in. So it has to be planar in sp2, or be able to assume sp2. This O can also donate in. So all 3 O's and all 7 carbons are coplanar, which means you have 10 atoms in the same plane. It's very flat. It can easily slide into cell membranes. So when we take aspirin in our stomach, the parietal cells that line our stomach lining, can actually have aspirin molecules migrate through the cell membrane into the core of the cell. But once it's inside the cell, the pH goes from 2, the acidic environment in the stomach, now intercellular pH inside the cell of 7.4. 7.4 is greater than 5. So like we said, deprotonated is greater than protonated. So instead of an OH, it's now an O minus. The problem is when it's an O minus, it cannot go back through the cell membrane. Ions can't migrate through the plane, or there's the lipid portion. So possibly go through a channel, but it's way too big for a typical protein channel, so it can't do that. And we don't have a transporter to bring it in or out because it's not a high abundant molecule in our body. So if it's not highly abundant, no need to have a transporter. So it can't go through a transporter, can't go through a channel, and can't naturally diffuse across the lipid, which means this is stuck. If it can't diffuse out, then our body starts bringing water into the cell to try to dilute it to get some sort of homeostasis. No matter how much water you bring in, you still have a higher concentration of this inside than out. So eventually it takes on so much water, the cell lyses. It ruptures. So if you hear that aspirin eats away stomach lining, it's actually simple acid-base chemistry. Hydrolyzes, under acidic conditions neutral, migrates into the cell. Under the neutral conditions, instead of acidic, it's now negative, can't migrate back out, sucks up water, causes the cell to swell and burst. So kind of a cool application of this concept of pK-pH relationship. So let me do the intuitive reasoning here. We have, if pH is greater, it feels basic. If it feels basic, things get deprotonated. So whether you're going to use Henderson-Hausbach and look at this mathematically, or intuitive reasoning and just say pH is low, protonated, pH is high, deprotonated, they both work, conceptual or mathematical. Both are perfectly valid. Want to add one last piece to the puzzle, so I'm going to have to erase everything to make room. And that is if it happens to be a case where pH equals pKa. I wish I wouldn't erase that Henderson-Hausbach because I kind of need it. pH equals pKa. If they're equal, then it has to be plus log of 1 because log of 1 is 0. so they must be equal. So protonated equals deprotonated. Intuitive reasoning, if it's not acidic or basic, it's going to balance. You're going to have a 50-50 mixture. Hopefully it seems okay. So this is our pKa pH relationship, and this is going to be kind of important in OChem, way more important when you start dealing with biochem. So pH less than pK, so this terminal or this carbonyl group protonated, carboxylic acid is protonated, less than 10, so that's protonated, and this group was deprotonated, all because of this relationship. Okay, again, if you are a math person, pH equals pK plus log of AHA, base over acid, deprotonated over protonated. So the math reasoning, if the pH is lower than pKa, if this is small and this is large, this must overall be adding a negative. It can only be negative if small number or large number, so protonated must be more dominant. So protonated is the denominator. Equally, if pH is greater, then this is larger than this, so this number has to be positive. I have to be adding. So log of a big number over small numbers. So the numerator this time is big. So the numerator is bigger than the denominator. Numerator is deprotonated, so deprotonated is a predominant species. So you can make this decision either based on the math or intuition. Make this decision based on math or intuition. Either way, whatever works for you, use the technique that works. So the math reasoning, if they're equal, pH equals pKa plus 0, log of 1 is 0, so these must be equal. Okay, that's our math part. Now I want to go into one more math part without so much, well, that wasn't really calculation last time, but we still had to decide what was bigger or smaller. This is just going to be straight definition. So we say an acid dissociates, breaks into H plus and A minus. A minus is off by itself. H plus can't float around by itself, so the water picks it up. So we'll say H3O plus hydronium. Equilibrium products or reactants, but little caveat, pure liquid for the solvent, the water. So notice water is not in the relationship. It's just the two products, conjugate base times hydronium concentration divided by the remaining acid. pKa, the P of anything, like pH is negative log of H, pKa is just negative log of Ka. Generally speaking, as Ka gets larger, because as negative, pK gets smaller. So if an acid gets stronger, it goes more in the forward direction. You're going to have more denominator, or excuse me, more numerator, less denominator, more product, less reactant. So bigger number over smaller number means Ka gets larger, but it causes pK to go down. So the correlation is acid strength goes up, causes Ka to get larger and pK to get smaller. The base can also react with water, but in case of a base, the base doesn't cleave. Instead, it cleaves water. So the breaking of water, known as hydrolysis. So second time we ran into that. A minus can come and take an H plus from water to form HA and leave a residual OH minus. Same arrangement as before, products over reactants, ignoring the pure solvent. Kb, negative log of Kb is the pKb, and then just like we do with H plus, the Kb is 10 to the minus pKb, this K is 10 to the minus pK. This is going to become somewhat useful math-wise for us. That's about the most important math we'll have. If the acid is stronger, if HA can go forward and generate A minus, that means A minus must be weaker. So if the acid gets stronger, the conjugate base gets weaker. So if the acid strength goes up, the base strength goes down. If the base gets weaker, we have a smaller numerator, so Kb goes down. Because it's negative sign, if Kb goes down, pKb goes up. So these all relate to one another. Stronger acid has a weaker conjugate base. Larger Ka, which goes with this, corresponds to a smaller Kb. So Ka times Kb equals 10 to the minus 14. And then if pK goes down, stronger acid, pKb must go up by the same amount. pK plus pKb add to 14. So overall, this is our relationship. Acid strength goes up, conjugate base goes down. Ka is higher, Kb is lower, pK goes down, pKb goes up. If I know any one of these 6, I know the other 5. And then pK plus pKb for the conjugate base, not the same compound, but the conjugate, equals 14 at 25 degrees. Okay, if this is going really fast, go back and take notes. The upcoming part is going to be more applicable to what we're going to worry about in OChem. So this is our background. The example I did with The aspirin in the stomach, that is more of a biorelated example that's going to pay dividends once you get to biochem. So make sure that you understand that concept of high pH, as in higher than pKa, deprotonated, and low pH, as in lower than pKa, protonated. Hopefully I said that right. Deprotonated at high pH, protonated at low pH. Okay, why these definitions become key? So let's say you're going on to take a standardized test at some point. I just want to point out then that for this one, I don't know what the question is asking me, messing with me. So I just have to look at answer choices. Higher ionization constant. So ionization constant is the products times one another. So kind of like a solubility product. This is an ionization constant, how much it turns into ions. So it's H0 plus times the conjugate base, but not divided by the denominator. But still, we have a correlation. If you get more H plus and more A minus, if it dissociates more, then it's a stronger acid. So higher ionization constant would mean more dissociation, ionizes more, which means more H plus, so it's a stronger acid. Greater dissociation implies, again, the same story. It ionizes more, it breaks apart more. If it breaks apart more, dissociates more, you get more H plus, stronger acid. Electron pair acceptor. So a Lewis base has two E's, so it's electron pair donor. So electron pair acceptor must be an acid. This saying a better Lewis acid means a stronger acid. Better acid is stronger. An increased pK, finally, something I can relate to. pH getting lower would be more acidic. pH getting higher is more basic. pKa getting lower is more acidic. pKa getting higher is less acidic. So increased pKa means it is getting less acidic, dissociates less. So for a question like this, even though I don't know what the question is asking, A, B, and C all complement. So D must be my best answer. Not that you'll see a question like this in your near future, but occasionally if you don't understand a question, but you have good vocab, you can work your way through a lot of multiple choice questions. Okay, so how are we going to apply it in this class? Not everything is going to be done in water, so I'm going to take advantage of what I know in water and then twist it a little bit. So we did HA plus water going to H0 plus and A minus to give me a Ka of H0 plus times A minus over HA, ignoring the water. If it was an acid like HB, it'd be the same story. HB plus water goes H0 plus and B minus, so I get the same thing. Numerator is H0 plus the conjugate base divided by the remaining acid. So this is Ka for HA, this is Ka for HB. What I want to do is I want to flip this reaction around. So instead of making this pair, these two my reactants, and these two my products, I make those my reactants, move those over, make those my product. So now it's H0 plus conjugate base going to acid plus H2O. When I reverse a reaction, when I flip it around, K-equilibrium products become reactants, reactants become products. So this number has to flip around. So HB is now the product, no water. H0 plus and B minus now the reactant, and it's 1 over KB. So if I were to add these two reactions together, let me make sure this works out. H0 plus cancels H0 plus. H2O cancels H2O, leaving me with HA plus B minus going to HB, and A minus. So when I add two reactions together, I multiply. So I'm going to multiply their K-equilibrium. I multiply the K-equilibriums, Ka times 1 over Ka. So Ka for HA times 1 over Ka for HB. So this will be my numerator, this will be my denominator. So K-equilibrium is going to be this times 1 over this, so I get that relationship. Plugging this in here, in this spot, plugging this in here, I'm going to multiply. H0 plus cancels again. So I'm going to have A minus times HB in the numerator, and then HA times B minus in the denominator. So A minus HB numerator, HA B minus denominator. So that's my K-equilibrium. So if I multiply these together, K-equilibrium for this reaction is this. So the water's dropped out. So in theory, this same reaction could occur if I used a different solvent than water, or if I did it in gas or a few other conditions. It may not work in those conditions very well, but I at least can get some sort of relationship. So this relationship is what I'm worried about in OChem for now. And acid-base behavior is going to predict chemical behavior in general. And so we're going to learn acid-base, revisit this reaction multiple times in different forms over the course of this class. Okay, so K-equilibrium then, let's go ahead and go with this. And this, hopefully, substitution makes sense. So when I was mentioning before that Ka is 10 to the minus pKa. So Ka here is 10 to the minus pK for HA divided by 10 to the minus pK for HB. Because it's in the denominator, if I brought it up, just like 1 over 10 to the minus fourth, it would actually be 10 to the fourth. The negative sign goes away when I bring it up. So it's going to be this, and that's negative. This will be positive. So if we notice, this, when it goes in numerator, now becomes a positive. This stays a negative. When you multiply numbers, you add their exponents. So a positive pK of HB minus the pK of HA. Notice that in this reaction, HB is your product acid. So that's your product acid. And HA is your reactant acid. So this is everything I was gunning for. This is the key equation trying to get out of all this review. So this is my OChem perspective. Okay, so what the heck are we going to do with this? This is where all my GChem math is going to be useful to support this one piece. That's all I take from GChem. This one piece is going to be useful to support some OChem reactions. So let's take that same reaction again, but let's toss some numbers in. Let's say this was a pK of 10, this is a pK of 5, and see what's going to happen with this. Lower the pKa, stronger the acid. Higher the pK, weaker the acid. So HA is my stronger of the two acids, HB is my weaker of the two acids. If the acid is stronger, its conjugate base is weaker, we mentioned that. And if an acid is weaker, its conjugate base is stronger. So this will be the stronger conjugate base, this will be the weaker conjugate base. Now it comes time for reactivity. A stronger acid is one that is more reactive and therefore less stable. A weaker acid is less reactive and therefore more stable. So stronger reagents are more reactive, weaker reagents are less reactive, but more reactive means less stable. Less reactive means more stable. Chemicals want to go to the most stable state they can, which means a reaction is going to want to go from the side that's less stable and finish at the side that's more stable, meaning this reaction wants to go in this direction, something more stable. So it wants to do that, meaning it favors the products. So I know K-equilibrium is greater than 1. Products are more favorable than reactants. K-equilibrium is greater than 1. If I wanted to, I can use the math we just learned that K-equilibrium for the reaction is 10 to the minus, or 10 to the pK of the product acid minus the pK of the reactant acid. So the product acid in this case is 10. So this is the number 10. And then the reactant is this. So it's 10 minus 5. 10 minus 5 is just 5, so 10 to the 5th. That is definitely larger than 1. So the math, once again, supports the intuition. That happened with our Henderson-Hausbach when looking at whether something's protonated or deprotonated. It's happening with this as well. If you want to blindly do math, because math is what you like, the math will tell you the result, and it's good. Or if you want to do intuition, stronger and weaker, stronger is more reactive, less stable. Weaker is less reactive and more stable. It's going to move from less stable to more stable, so you can predict it's favorable in the forward direction. K-equilibrium is greater than 1. Both of these methods work. Both these are perfectly valid. One note of interest when I say K-equilibrium is what it is, greater than 1 simply means products are more favored than reactants. This one is more specific. Still the same result, greater than 1, but simply means I favor the products. So let's look at another one. HJ, again, random letters. A and B don't mean anything. J and Z don't mean anything. They're not elements. I have to be given some information. So now my pKs are a little more specific. 8.43 and 6.11. 6.11 is lower, so HZ is a stronger acid. 8.43 is higher, that's the weaker acid. So weaker acid with a higher pK, stronger acid. I already went through all this before, so if you want, you can just say stronger to weaker. I'm done. I know it has to go backwards. K-equilibrium is less than 1. But let's be thorough. Weaker acid has a stronger conjugate base. Stronger acid has a weaker conjugate base. So weaker conjugate base, stronger conjugate base. If they're weaker, they're less reactive. If they're stronger, they're more reactive. And then less reactive is more stable. More reactive is less stable. Things want to go to stable, so this one wants to go in the backwards direction. K equilibrium is less than 1. That said, I can go ahead and plug into this product minus reactant. So 10 to the 6.11 minus 8.43, which in this case is a negative number. It's negative 2.32, it looks like. So again, this number corresponds, it matches. Okay, where we're going to go from here. I'm going to terminate this lecture at this point, but what I want to do in the next lecture, it's also going to be on acid base. We're going to start, instead of looking at generic HAHJ, ZHB, we're going to start looking at specific acids. So just like I mentioned earlier, carboxylic acids, to give an example, those have pKs around 5. Phenols, we learned, have pKs around 10. So this becomes somewhat useful. Protonated amines, RNH3+, have pKs around 10. Usually it's like 9 to 10. Thiols are usually a little bit higher than 10. So I'm going to say 10 plus, a little bit. Those be 10 minus. But if I start asking you if a carboxylic acid reacts with a phenol, carboxylic acid reacts with a thiol, a protonated amine and a phenol, I give these combinations, you should be able to take these numbers and predict what the power will be. Or in the opposite sense, if I give you 2 compounds and tell you come up with a certain number, you should be able to work backwards and figure out which is a stronger acid. So we're going to study which one is a stronger or weaker acid, and we're going to use this K-equilibrium approach to determine if we're right or wrong. Hopefully this is nice and smooth sailing so far. This is, again, a lot of background information, but we have finally reached a point after this podcast that we're actually going to start getting more and more into the actual content of OChem. So hopefully this is excellent for you. I'm going to go ahead and stop this, and we will get together soon. Thank you.